Hello and welcome to my presentation about using machine learning to automatically find quantum algorithms, brought to you by myself, Evan Garber. Let's begin with what quantum algorithms and quantum computing actually entail. At the heart of quantum computing lies the qubit, which is the quantum analog of a classical bit. Classical bits run everything like your computer and phone and all modern technology that you use. They exist in either a 0 or a 1 state, representing the off and on states respectively. However, qubits can exist in a state that is somewhere in between 0 and 1, being a linear combination of both 0 and 1 at the exact same time, which is known as superposition. Just like normal logic gates that operate on classical bits, such as the AND, OR, XOR, etc., there are quantum gates that do similar things. The X gate, for instance, flips a qubit's state. The Z gate changes a qubit from 1 to -1, and a special gate, the Hadamard gate, or H gate, puts a qubit into superposition. All quantum gates are unitary and can be thought of as rotations around the Bloch sphere pictured here. There are many other quantum gates as well, but they won't be mentioned here. Qubits also have a unique property known as entanglement. When two qubits become entangled, their states depend on each other. This means that if we measure one qubit and take a measurement of another qubit, the second qubit's state will depend on whatever we measured from the first qubit. There are certain gates that can apply to multiple qubits that will entangle the qubits together. The controlled NOT, for instance, the C0 gate, flips the target qubit if the control qubit is in the 1 state. The controlled Z or CZ gate changes two qubits from the state of 1,1 to -1,1, but this only happens if both of them are in the 1 state. Now that you have a basic understanding of qubits, let's talk about machine learning. A neural network takes a list of inputs, applies some algorithm, and then provides an output. It then compares the output to a desired output, and then it makes adjustments as necessary and runs again. It does this process hundreds or even thousands of times until the model is very close to being correct. You may be wondering how all this fits together though. Well, it turns out that you can make any quantum gate using a very specific combination of rotation gates combined with CZ gates. For example, the C0 gate can actually be made using two Hadamard gates and a CZ gate in between them. We can use this property to construct a neural network that can adjust these rotation gates, so imagine instead of an H gate we have a unitary gate that is completely arbitrary that we can change. The next question is what combination of different unitary and CZ gates works best together. I've created several circuit designs and tested them by having them learn the quantum Fourier transform. There are also two different randomly generated circuit designs that are not shown here. It's important to note that these blocks of circuit were repeated dozens of times, resulting in hundreds of adjustable gates that the model can change. Below each circuit is the fidelity or the closeness of the neural network in correctly applying the algorithm, with one being a perfect match. These circuits are all pretty dang close. So you may be wondering which circuit is best. Well, it depends on our criteria. Because each circuit can obtain an arbitrary closeness, we can look at which circuit performs the best using a set number of gates. To test this, I set each circuit to have approximately 200 gates and then recorded their fidelities. This design here had the best fidelity, using 200 gates. Another criteria we could look at instead is the minimum number of gates required in order to reach a certain fidelity threshold, such as 50%, 90%, and 99%, seen in this graph. Once more, the same circuit was the best. It reached 99% fidelity using the fewest overall gates of 210. However, in some physical quantum computers, it is much easier to apply unitary gates than CZ gates, as entangling qubits can be quite difficult. With this in mind, we can see that this circuit over here actually required the fewest number of CZ gates and still reached 99% fidelity. Interesting. So, why is any of this important? Well, when we want to develop better quantum computers, we have to take into account the physical resources required. Using single qubit rotations and CZ gates could offer advantages over specific entangling gates, as they may be easier to execute. Additionally, having an adaptable circuit means that the scientists wouldn't need to physically adjust their quantum computers in order to run a different algorithm. As the field of quantum computing is continually growing, scientists will always be looking for new and better ways to run their algorithms, and this research discusses just one of the many potential paths to more efficient quantum computing. I'd also like to thank Ben Bartlett for his guidance and support in this paper and research. Thank you.